Hi, welcome to the Joshua's World Academia sessions. And this session, as I started off just very soon, I would like to just repeat in short that it's a very basic understanding session about CC3220, which is a simple link Wi-Fi SoC provided from Texas Instruments. And this particular microcontroller is very useful for all you guys out there who want to develop some kind of wireless communication or IoT communication platform. So today in this session, like in my previous session, I have already given a brief about how to connect the launchpad, the 3220 launchpad with CCS running in a laptop or a PC. Please refer to my previous video for that. And in this particular video, we will be considering a basic architecture of the CCS. So let me see like what are the points or what are the chapters that we will be considering for this particular video and the next videos. So this is this particular document I will be following, which has been provided from Texas Instruments, and this is a very useful document. This tells you all the details, and you must go through some part of it before you start working your hands on with the processor. And I will just guide you through some of the libraries and some of the examples that has been given by Texas Instrument in the Simple Link Academy folder. It's a very lucid and easy to understand system platform and examples. So if you guys are aware of microcontroller programming along with some basic features that are provided by various wireless network processors, you should be able to go through it easily. So let me start off by explaining what are the topics. Okay, first just remember to download this particular document from the net. You can just search Google by writing SWRU 465. This should give you this particular literature, and then after that I would just tell you that what are the important topics or points that we would have to cover. Now the very first thing that I would like to go through is the architecture overview, because you must know what are the different parts of this processor. Like I am totally against this kind of approach that just first some people do tell to just download Code Composer Studio and then install Simple-Link SDK, and then just run some example application. For example, you are supposed connecting a SPI slave, so you just run a example configuration of SPI, and then you do delta programming, bit of delta programming for that, and that makes. But in that particular learning process, you will not be able to understand that what are the basic features and how you can tweak with them. You have to rely on the core platform that is provided by Texas Instruments, and I'm afraid to say that that would not let you develop your own system and do your own application programming or even driver development. In case if you want to customize some drivers, it would not let you do that. So you must go through the architecture overview. So the architecture overview is one important topic. Inside the architecture overview, there are some important things that we need to consider, we need to learn. First is obviously the GPIO function, and as we know that GPIO stands for General Peripheral Input Output. So if we come down to the GPIO section, this is the GPIO section that describes what are the various GPIOs. We won't go much deep into the registers. As you can see, of course, there are a lot of registers, right? I'm just highlighting them for you. So there are a lot of registers, but all these registers are unimportant for us because we will be using straight away TI driver libraries, which are provided inside TI RTOS, that is Texas Instrument Real-Time Operating System. So people out there who want to follow your own RTOS, like for example, if you are not using TI RTOS, if you are using FreeRTOS or any other RTOS, so for at least for FreeRTOS, TI do give these driver libraries to be integrated with FreeRTOS. But in case if you're using some other RTOS, then you have to browse through the TI website to find the GPIO driver library for this particular microcontroller. But I would suggest you that for students or learners out there or beginners who do not have any kind of idea as to how we integrate a driver library, or those who want to do their own bare metal type of programming, that is no RTOS or without using any RTOS, I would suggest them that please be very careful while doing memory management, because and also other managing other different kind of use cases that will arise, because these are ARM Cortex M processors. There are a hell lot of libraries, sorry, I mean there are a hell lot of registers for each and every peripheral, and there can be some minor to severe problems that can be affected in your system. For example, for GPIO, if you are not using a TI drivers, then let me for example let us consider a pin which already I will just explain to you with the help of a diagram. Okay, so let me consider that this is a this is a CC double C 3220 chip, and here is your maybe the GPIO peripheral. Okay, now what I am speaking is that there is a one particular pin. Okay, so let me just assume any pin number, say PA1 for example. Okay, now this PA1, this particular pin, say the pin number is say 5. Okay, now this pin is multiplexed, there's some kind of mux driver. Okay, so there's some kind of mux driver, and this mux driver will control whether this pin will be connected to the GPIO block, or it will be connected to some other peripheral. And for our instance, let us consider that to be ADC. Now please remember that CC3220 has an ADC pin sensitivity of 1.5 volts. Okay, it is also recommended to be kept within a range of 1 point, I would say 1.5, but it is recommended to be kept in the range of 1.8. Now suppose if we have a GPIO pin that is connected, that is if you have configured the mux in such a way, I will just use a more broader color, and suppose if you have configured this particular pin in such a way that you have just run it to the GPIO section, so you are handling maybe some 3.3 volt. Okay, you were handling some 3.3 volt. Now due to some requirement in your application, you choose to just cancel the configuration of the mux register, and you want to channelize this pin to ADC. So that is very much possible, but as soon as you channelize it to ADC, and if 3.3 volt falls inside your ADC becomes damaged, and that is a very 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 dangerous thing. Your ADC will become damaged if you give a direct input of 3.3 volt. This is very dangerous because remember, in this particular chip you do not have unlimited number of ADC channels. You have only user applicable 4 channels. So there are, in this particular ADC input, you have only 4 channels that can be used by user, and there are 4 dedicated channels that can be used by the internal system. So this is like the internal, and this is the user. So the process for shifting from the GPIO to the ADC configuration is like a break make. So first you have to break this particular connectivity. Okay, and then you have to establish this particular connectivity. So that is what I would like to tell you. Now let me go back to the datasheet once again. Okay, so that was the thing which we need to take care for those guys who are planning to use not to use any RTOS. But since we are using RTOS, we do not need to bother so much about the registers. So after doing the GPIO section, I would prefer to come to the ADC section. Just a second, that is a bit lower. Here is the ADC section. So after doing the GPIO, I would immediately go down to the ADC, because Rest of the sections, like for example the peripherals, for example SPI, I2C, UART, those three I will cover in one single video because they are mostly dependent on communication, and UART and SPI as well as I2C, all three of them, the pattern and the communication type and configuration types are almost the same. So these are the two important topics, ADC and GPIO, along with a basic architecture that I will be covering in this particular video. So guys, let's start off. Hi, so here you can see that this is the page. You can just scroll down to this page number 36. So here I would just, it will become immensely boring if I go through the datasheet. That is, you can read at your spare time, but I will just highlight some points. Just listen to it, and I am sure that that would be enough for you to grab into it right now. So just remember one thing, that this particular device, that is CC3220, is a platform which supports Wi-Fi, BLE, sub 1 gigahertz, and other host of MCUs. So it's a simple link platform, basically helps you develop in all these kind of environments, that it helps you to develop in Wi-Fi, it helps you develop some kind of BLE application, it helps you develop some kind of sub 1 gigahertz application. And the beauty, or the most important part, is that you can just change your MCU according to your requirement. And if you have a simple link application which you have already developed, so that application is totally portable, apart from a few basic configurations that has to be done. So we are going to select the simple link platform for the CC 33220 chipset chip. And if you want to make your design more robust, you can see TI's website, where you can find some other multi-standard processors as well. As of now, 3220 will support only Wi-Fi, but there are devices like 3235, 1352, who can communicate over multi-standards. So these are some basic applications there where you might find interest if you are looking into some broad spectrum application. So next we come down to the most important point, is the 80 megahertz part, that is this particular processor core, which is an ARM Cortex M4 core. Now I will not be going into the depth of the ARM Cortex M4 core, because ARM Cortex M4 is a design that is described and sold by ARM. So you might have to search. You can search in the internet, or wait for my later videos where I can just describe the basic features of what is an ARM Cortex M4. So this particular processor has two ARM Cortex M4 cores, as I said. So the application one, that where your program will be running, it runs at 80 megahertz. That's quite a high speed, and it has very good MIPS value. And the peripherals, it also comes, this chip comes with a number of good number of peripherals, as I was saying. Some important ones are like fast parallel camera interface, as I have shown over here. That is, you can directly connect a camera to that particular camera interface, and you can stream your own video over the IoT platform. And since your web server can also be hosted inside your board, so you don't have to depend on a third-party hosting system. So this is one very good application, that is a very fast parallel camera interface, which can help you develop some kind of AI application if you're planning to send the video into the cloud and do some kind of data ingestion and some kind of processing out there using. And one thing more also, SimpleLink 3220 does have an AWS and Azure IoT plugin SDK, so you might look into it, and you can just have your own choice of some APIs over there which you might want to integrate. There is also an I2S platform. I2S is used for for digital sound applications. If you are developing some kind of audio DSPs, there you will be finding I2S applications. Okay, so the next one is the SD application peripheral. That is, if you're interfacing any kind of SD card, so you can use it for your SD card communication in RAW format or simple file format. There is only one bit 0 format that is allowed, I guess. So we'll see to it when we go to that particular peripheral tutorial lecture. UART is, as we all know, that it's the Universal Asynchronous Receive Transmit section for the RS232485422 and some other kind of communications. There is also SPI. There are two SPI channels. You can use two SPI slaves with this particular system. And for those who have a specific SPI application, for example, if you want to communicate this chip with some other kind of RF slave device, for example, if you're integrating some other third-party manufacturers RF front end, then two SPI channels will be very helpful for you. So there are basically two SPI. So one thing you have to remember, that this particular SF family, 3220 SF family, they have one SPI dedicated uh, to specifically to the flash, XIP flash, wherein you can use the application and you can host your web page. And there is one particular SPI which is totally dedicated for the user applications. So these are the two important things that you have to know. The I2C, there is one I2C is a ubiquitous application for our system, and we all have to use I2C. So I2C peripheral is also there, and it supports most of the modes that we use in I2C. We'll come to it later. So, and there is a 4-channel ADC. So this is what I was telling you, that it has a 4-channel ADC and not a multiple like 15 or 16 channel ADC as we see in other ARM Cortex microcontrollers. Okay, now one important point about this was all about the application system. Now we come to the next part of the ARM Cortex processor. As I told you in my previous video, that there are two processors inside. Okay, so the one part, that is your application. The other part is the network processor. So the network processor is a pure internet on a chip solution. So basically you have all the internet related socket communications and internet related features that is available directly on your SoC. And there are some important points that I would like to mention, is that the most important thing is that this chip gives you 256-bit encryption. Obviously, if you're going for the CC3220S or SF, you will be having a encryption. And this device also supports a station mode. It supports a station mode, it supports an access point mode, and it also supports a Wi-Fi direct mode. So you have three modes that is supportable by this particular MCU system. Now the device also has a WPA2 personal and enterprise security and WPS2. So these are, for example, if you want to connect directly to this chip to a Wi-Fi network, and if your Wi-Fi network SSID, you have the Wi-Fi network SSID, and the password is like, say, WPA2 with a personal or enterprise level security. So that kind of security encryption is supported. So you can directly connect this chip to a Wi-Fi network, and since it has its own embedded TCP IP, so this chip gives you its own embedded TCP IP stacks, SSL or TLS secure channel stacks. You can host your own HTTP server and also some other multiple protocols. So basically you can develop your own internet application directly using this chip. You don't have to write your any kind of application layer for handling, or mid layer for handling this kind of stacks. So that is a very basic overview that I would be sharing. Now let us come to this particular figure. Although this figure is not of much importance, uh, but some points are good just to just browse through, is that you can see over here that flash, I2C, camera interface, SD card interface, then GPIO. There are 4 GPIOs, as you can see: GPIO A, GPIO A0, A1, A2, A3. So there are 4 blocks of GPIOs. So all these pins, even the timers, here the two UART, UART-A0, UART-A1, and the ADC. So all of them are, you can see that on the left side, these are the pins. Right, so these are the pins, and on the left side you have the pins, and there is some mux controller. This is the pin mux controller, as I was telling you. You can see it, I've highlighted. This is the pin mux controller over here, and all of the pins can be muxed to communicate with the particular port which you want. So this is one beauty of this particular design of this ARM Cortex design. And there are two buses over here as we have for the ARM architecture. One is the advanced peripheral bus, which is obviously a low performance bus, because APB is for those peripherals which are not demanding some kind of high, high speed communication. For example, ADC, UART, and timers, and other kind of peripherals which do not need a very high speed communication usually. And there is also an AHB. So as we have in ARM, in ARM architecture, you might be aware that there are two buses which are used, that is a part of the AMBA. So one is the advanced high performance bus, that is AHB, which communicates with high speed peripherals, as you see over here, I2C, SPI, flash. This flash SPI is connected. This flash SPI is what I was talking to you. This is connected to your external flash if you're selecting the SF section, SF type, and this is the application SPI. So these two are high speed peripherals. So AHB is a high speed communication bus, and AHB also lets you interface your GPIO, and you can blink or toggle a pin at the rate of the system frequency. So this is really something that is a beauty of the ARM architecture, and this is possible if you go for advanced high performance bus. But nevertheless, there is also, if you come here, there are two bridges over here. You can see these two bridges are nothing but, they just bridge the two type of buses. Suppose if you want to bring data from one particular peripheral to another peripheral, then you have to use something that is called a DMA or a micro DMA, that is direct mode access. So in DMA, what happens is that your core is free to do its own application, but the two peripherals can communicate. For example, you can program the DMA to pick up some data from the ADC sensor channel and constantly send it over the UART, or maybe constantly save it into an SPI EEPROM, or maybe constantly even send it to an SPI slave. So you don't need the processor intervention. The micro DMA can take care of it, and there are several micro DMA channels, and you can dedicate a channel to a particular, say, ADC channel, and that particular channel will take the data from the ADC whenever the conversion is complete, and it will perform wherever in the memory, whichever peripheral it has to deliver. So this is something really a very good feature out there. Coming on the lower part of it is the RF section. So in the RF section, there is nothing much that I have to say. So those of you who are quite familiar with RF designs, you can see that there are two crystal oscillators and a few LC arrangements. So these arrangements, one thing is very important for you people to note, is that if you guys are planning to make your own board with this particular chip, so first you can, after trying out with the Launchpad your application, once it gets stable and freezed, many of you might like to develop your own board with this particular chip. So please follow the design guidelines that are given in the design data sheet. And I would like to mention it. It is there in this particular document as SWRU 555J 455J. So you have the hardware requirements, because these LCs which you can see over here, like for example an inductor is here, then capacitors are here, these are all for RF, proper RF operation. So there are some requirements, there are some track running routing requirements which must be followed. So please take care of that if you are planning to make your own system. Okay, so the crystal, there are two crystals over here. One is 40 megahertz for user for running the system of the RF and generating 2400 megahertz, the baseband for the RF communication. And another crystal is there which is a low frequency crystal, and that is used for generating the clock signal for running your peripherals. So more or less this is what I would like to highlight as of now, of the design. The rest is up to you, you can go more depth into it. So just This is just basic. Okay, so next I'm coming to the ARM Cortex core. We have to remember that it supports thumb 2, that is a 16 and 32-bit instruction set. That is another important point. You can communicate with a 4-pin JTAG or a 2-pin JTAG, like uh, like over here. They already, in my previous video I have showed you that they already have their own JTAG. So for JTAGs you don't have to bother as of now if you're buying your launchpad, but if you're making your own application, then you can buy an XTS 110 hardware from TI, and you can select whichever mode you want. You can use a 2-pin JTAG or a 4-pin JTAG. Also, there is a SysTick timer. The SysTick timer is very important for RTOS because you need a specific clock ticks which you can use for various kind of applications in your system. So there is a particular a peripheral which is a system timer, or we call it SysTick, that generates a sample 100 hertz frequency that can be used for various kind of SysTick applications in your RTOS. Now this processor also supports nested vector interrupt controller. So you, like for NVIC, I won't be explaining much over here, but just to tell you one thing is that nested vector interrupting is like, for example, let me show you with a diagram. Okay, so just to understand like what happens in a nested vector interrupt controller. For example, your program is running in a main loop, for example, and this is the primary code which is lying, or maybe this is a particular, say, uh, any particular task that you have configured. It may be idle, or it may be some kind of thread that you spawn, or multiple threads, whatever it is. So whenever an interrupt comes to your processor, suppose there is a UART interrupt, okay, and let us assume that the UART interrupt has a priority, say 5. Okay, so the processor immediately, what it does, from this main loop, it will go to the interrupt subroutine. So before going into this interrupt subroutine, what it does is it takes some backup of the processor state and some vital registers. So for that you have to, if you want to know what are the details that is taken as a backup, you will have to study more detail of NVIC in ARM architecture. So as of now, you can just remember that some data are pushed into the stack. So you just push into the stack, and what you do is you enter the interrupt subroutine. Okay, so this is say ISR 1. Now when you are entering into the ISR 1, suppose there is another interrupt. Suppose there is an interrupt from, say, some more vital location. For example, say there is a SPI interrupt. Please don't go into the criticality of the priority right now. Maybe what I'm saying, the priorities in the datasheet might differ, but just try to understand what I'm saying. Suppose we have a SPI which has a priority 4. So what will happen in this particular NVIC, there is a support for tail chaining. Tail chaining means as soon as ISR 1 gets completed, the processor will not return to the main loop. It will not do this, because doing this will lead to a pop, that is taking back from the stack. Okay, and since there is one more interrupt is waiting, so it again has to go to ISR 2. So what happens is that it will be just popping and then again pushing, because this will be a push operation again, because this is another interrupt. So basically the register values which it is popping and pushing will be almost the same, rather it will be the same. So basically it is saving a total of 12 clock cycles. So it is basically saving 12 clock cycles. So 6 for here, and six clock cycles here, and 6 clock cycles here. So by saving, by instead of doing this pop and again push and then going to ISR2, what it does is it directly jumps from ISR to ISR1 to ISR2. That is called tail chaining. Once ISR1 gets completed, it goes into ISR2. Now similarly, if you have another interrupt, say you have an interrupt from even more higher priority, say from a non-maskable interrupt pin NMI, which has a priority say 1. So that is a very high priority interrupt. So what it will do again, instead of going from ISR2 back to main, it will just jump to ISR3. So ISR3 is the ISR for NMI, so it will jump from ISR2 to ISR3, and thereby 12 clock cycles are saved over here, 12 clock cycles are saved over here, and thereby your interrupts will have a limited latency, or there will be very minimum delay. So this is something that we must remember. So once ISR3 gets completed, it can directly go back, and now when it pops out from the stack, you can see that it will basically pop out these values over here, because the in between push and pops are unnecessary. So this is one important thing that is there for tail chaining. Also for preemptive interrupts, for example, if there is, I will show you a preemptive interrupt. For example, if the processor is running at in a particular ISR, suppose if this ISR is running ISR1, that is interrupt subroutine 1, your processor is in interrupt subroutine 1, there is a more higher priority interrupt which has come. So what it will do, it will jump to, from ISR, it will jump directly to ISR2. So this process is like preempting meaning like you are not finishing the ISR, you are jumping to a higher priority ISR. And it also may happen that in ISR2 you have another interrupt which makes it jump to ISR3. So once ISR3 completes, it goes back to the same path it had followed, that is ISR2. It completes ISR2 and goes back to ISR1, and it completes ISR1, and then it goes back to the main loop. So this is again a preemptive type of an interrupt subroutine. Here also you don't have to multiple times, you don't have to save the state of the processor, you can just jump from one state to another. But these preemptive type of interrupt, I would request you to go through the details of the ARM architecture. Okay, so now we are back. So now you understand more or less what is it. So you can just go through this part of the system. Next, let me come to the on-chip SRAM. This is very important, is that there is 256 KB of zero wait state. Now what is zero wait state? Zero wait state is like you do not have to take a lot of time to write into your flash or your SRAM. So let me give a more detailed explanation on this. Okay, so to understand the zero wait state, let us take this example. For example, this is a memory location. Okay, this is a memory location which you want to access. So these are the memory cells, and remember that there is your ARM Cortex CPU. Suppose this is your ARM Cortex CPU. Your CPU is running at a certain frequency. Suppose if your CPU is running at a frequency of 80 megahertz. Okay, and your CPU will be processing the instructions that you have written for it, and that processing will have some kind of time, which let me denote it as a processing time, PT. Now if the processing time is, say for example, is say 0.1 nanosecond. Okay, if the processing time is 0.1 nanosecond. Now, zero wait state means that suppose at 2 points of this particular operation, at this point and at this point, you need to perform some kind of memory access. For example, at this point you access this memory location and you write something, and at this point you retrieve that value, for example. So there are two memory operations. Now let us consider one interesting fact. Like, if this memory, whatever memory this you consider, for example, you can consider this as an external memory or internal memory. If this memory, we all know that all memory chips, they need to be supplied with some kind of clock frequency to operate. So suppose if this memory is operating at a speed of say 40 megahertz, right? So what will happen? Your CPU is processing at 80 megahertz and you are having a processing time of say zero point 0.1 nanoseconds, but this particular memory cannot do this particular. So your looping time is say zero point 0.1 nanosecond. That means in zero point 0.1 nanosecond you are writing this operation, also reading the operation, but your CPU, your memory cannot be so fast. Maybe it takes say 2 nanoseconds to do a read write operation. Okay, it takes 2 nanoseconds. So this particular writing will take 2 nanoseconds of time, and this particular writing will also reading will also take 2 nanoseconds of time. So what will happen, even if your processor is running at a very high frequency and your processing time is very fast, that is say zero point 0.1, even lesser than 1 nanosecond, you have to give a window of 4 nanoseconds to 4 nanoseconds to access into the memory if you want to do a read and write operation both. If you are only doing a write or only a read, then it is half of that is 2 nanosecond. So this difference is, this type of state where you have to wait till the memory is accessible, is called a wait state. So here in our application, here in our application, it is a zero wait state, meaning that the processor is processing at you can say that the processor is almost at par with the processing power of the RAM or the internal memory. So the 256 KB of memory is in a zero wait state. So this is something very 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 helpful for you if you are, if you have some kind of application where you would like to save some kind of data, and that data has to be acquired from some slave, and which is a really fast operating slave. So that is very important for you. Also apart from that, there is you can just go through this on-chip SRAM. This is something that I would like you to read each and every line of it. There are also some low power deep sleep modes. This is very useful if you are developing any kind of battery power application, because this chip supports several kind of low power modes. One is the LPDS, that is low power deep sleep. One is the hibernation mode, and the other is the normal low power mode. So each of them have their own RAM retention capability, and you can choose to save, you can choose to retain 64 KB of RAM, you can choose to retain 128 KB of RAM, you can choose to retain even up to 256 KB. So that is a total RAM retention policy that you have, and you can just go through, you have to go through the detail of the power management framework. Okay, now let me come to the ROM. So in the ROM or the flash memory, just a very small thing that I need to tell you is that, if you are choosing the SF version, then you have up to 1 MB of XIP flash which you can connect, and you can keep all your data related to your application code in this particular flash memory, and from here you can run your own websites, your own web pages, and other kind of application, whatever you might need to databases or whatever it is. So this is a very very useful thing, and it is organized in as a sector of 2 KB, so you can access it in forms of 2 KB sectors. And the other is the normal versions, which do not come with this particular capability of flash memory. So there, your ROM, which is again, as I said, is a zero wasted, which means it's a very fast, very fast ROM. So it is already preloaded with some peripheral drivers. So this is something which is very important. Just listen to this very carefully. If you need to use any of the peripherals inside the chip, you do not have to load the driver in the memory area of the ROM where you're storing your code. That is your text section. You do not need to waste space, although it is inside a flash or ROM, for a peripheral, because there is already a memory section or a ROM section which is preloaded with the peripheral driver libraries. So this is very, very, very important. I would rather mark this as red. So this is something that is very, very, very important for you to remember, because you do not have to load unnecessary code into your chip for interfacing the peripherals. Now there is also bootloader. If you want, you can customize your bootloading, and if you would like to go in for a device software upgradation. So this we will see when we will discuss the bootloading. And so this is kind of you can also have a OTA, that is over the air firmware upgrade, as we have for our mobile phone. So that facility we can have. And there is also device initialization, which is also stored inside the ROM. So ROM basically consists of these three things. So that's important. Okay, micro DMA I have already explained, I won't go deep into it. There are general purpose timers. This also is a very basic fact that most of you know. So let me not waste time right now into all this, because I will be covering each and every section of all these in separate videos. Watchdog timer is also very important. So watchdog timer can also run in a watchdog mode or timer mode. So all these things we will come on. We have a multi-channel audio serial port. The MASPs will help you to develop some kind of audio DSPs, in case if you are using some kind of codecs, or for some MP3 applications or some audio applications. So you can interface some DAC and codec for reading or streaming a wireless audio file. In fact, you guys will be very interested to hear that there is a particular there is a particular application which is there inside your simple link examples, which is called a wireless audio. So just go and check it out. It's a very interesting thing. You can design your own wireless speaker system in your room by using only a pair of launch pads. So, and I think there's one more booster pack that is required. So that is a very interesting project wherein you can do your own audio, your own wireless audio product, and you can use it with your own laptop. So you can just check it out. That's an important application of the audio serial port. SPIs, I have already told you, it has a frequency of up to 20 megahertz of operation. So this is very, very interesting. Like 20 megahertz is quite a high speed. It is good for interfacing some kind of fast slaves. Okay, I2C, as usual, we have the 100 kilohertz or kbps mode, and the 400 mode, and the addressing mode is 7-bit. Okay, so UART also I am not doing right now. So we come to the most important point, that is the GPIO. So let me just give you a very basic introduction of the GPIO. We have a total of 24 GPIO pins. That is, 8 pins are there, and it is like segregated into 4 I would say peripheral slots. Okay, now let me just go through it. There are 4 instances of GPIO modules. That is like mm, this would be rather like I would explain it like for example, 4 instance means, if you just imagine a class, and if you just instantiate 4 objects of that class, it is an ideology like that. And each having 8-bit, so up to 24 GPIs you can use. There are I mean, there are some limitations in the pin, because this particular chip also needs some pins for the RF connectivity. So there are up to 24 is only possible. Interrupt capability is there. So you have 2 type of interrupts. One is the level sensitive. For example, if your pin voltage is detected as 3 volts, then also you can, that is 3 volts means if it remains in 3 volts, so for as long as it remains in 3 volts, you can have interrupts. Or you can also have a 0-volt interrupt, that is a level sensitive interrupt for high and low levels. Also there is edge sensitive. For example, if there is a transition from low to high, then also you can generate an interrupt. Similarly, if there is a high to low, then also you can generate an interrupt. Okay, so and also you can mask some interrupts. So all these details we will see later on. we can trigger DMA operation. That is, for example, if you have a DMA channel that is configured, and from that particular DMA channel you want to control it. Suppose if you have, let's say we have a DMA channel. At one end of the DMA channel we have a ADC, and in the other end we have some memory area, and you want to control the DMA with the help of a GPIO pin, that if a signal comes to the GPIO pin, the DMA will operate. So that you can do. This is what it is explaining. Okay, now let us go to the GPIO section. A very brief introduction of the GPIO section is like there are 4 ports. As I said, there are 4 instances, A0, A1, A2, A3, and 32 programmable input-output pins. But there are some limitations in the chip due to the RF. So up to 26 GPIOs depending on the pin mux configuration, and excluding the 2 SWD pins, that is the 2 JTAG pins. You have to exclude the 2 JTAG pins, and also there is a diversity selection for the antenna switch control. So 4 pins you have to leave for that, and also there are some pins that needs to be removed for the 2-wire JTAG sense of power and the 4-wire. So all these things will require some pins which cannot be used for normal GPIO, and that is only limited up to 26. That is the reason why it is limited up to 26. Okay, now interrupt I have already shown. Now very basically this is how the GPIO looks like, and the pad is the pull-up section. Okay, so for example, if you would like to configure the interrupt, you would have to go for these registers, the lower ones. If you would like to configure whether it is an input or an output, that also will be configured in the digital IO pad, and the data control will be controlled over here in the upper part. So basically this is a very like basic diagram of the GPIO section. Important point to note is that how a GPIO output and input functions. Now in CC3220 we have a very interesting way of updating an output. So this you have to listen very carefully. Although since we will be using GPIO init in our RTOS and we will be using the standard libraries, we don't have to bother, but it is very important for those who would require to appear for interviews, and this can be a very important interview question. So let me just go to it. Now let me first read it out, and then I will show you in a diagram. It says that during a write, if the address bit that is associated with the data bit is set, the value of the GPIO data register is altered. What does this mean? It means that your GPIO register has a particular address, that is 0x98. Now, in ARM architecture, each and every register has an offset. There is a base value, for example, GPIO A. I'm just giving you an example. Suppose GPIO A. GPIO A might have a base value, and that base value can be say 4000.0000. So from that address, the GPIO data register will have an offset. So basically what they are trying to say here is that, for example, if your address register is this one, that is 0x98, so the bits, the last few bits will be, that is from bit 2 to bit 9, will be 00100110. Okay, and if this is the data which you want to push into your GPIO data register, that is the output which you want to see, then the internal architecture will compare that which bits of the address is 1, and the bits of the address which are 1, only for those bits the data which here is 0xEB, only those bits will be pushed into the output. I'm sure most of you must be confused, because even I was when I first read. So let me just describe this in a diagram. Okay, so let me just try to explain the writing operation which is followed by TI in this particular design, ARM Cortex M4 core. For example, like this particular GPIO, it has a base address, so I have just assumed a base address of 4000. It will be, sorry, I have missed 10. It's like 40000000 plus 98 is the offset, as I was telling you. So if we compare the last 9 bits as I have drawn on the right, you can just see it over here. I've drawn on the right. So if I write the address value over here, the last 9 bits of the address value, it will be something like this. And the 9 part will come like this: 1001. And obviously the upper two, the bits number 8 and bit number 9, will be 00. So this is how we will represent the 98 part of the address in the register. Now what this particular design does is that, suppose if we want to write this value, let me consider the value as 0x7b. So 0x7b in binary would be this. So let me just write the binary values. The binary value will be 0, 111 and 1011. Okay, so according to the TI, this particular architecture or the core architecture of 3220, what it does is that in order to write these values to the actual output pins, you have to consider only those bits of the address which have been set as 1. So this bit is set as 1. Okay, this bit is also set as 1, and this bit is also set as 1. So we will only consider these bits. So if we do a direct map between the data and the address values, only the bits in the address field which are set to 1, those bits from the data will be pushed into the actual output pins. Means that since this bit is 1 in the address, so this value will be pushed into the output. Again, since this bit is 1, bit number 4 is 1, so this 0 will be pushed into the output. And since bit 3 is 1, this 1 will be pushed into the output. And all the other bits will remain unchanged. So if we write the final output value, uh, it will be like unchanged, unchanged, unchanged. Again, this is also unchanged, and this is also unchanged. And this value will be 1, this will be 0, and this will be 1. So this is how the output will appear in this particular design. So this they have done because this operation takes very minimal time, and this will help you achieve a very high speed updating of the output port. So I hope you have understood. Now let me go back to the data sheet. Okay, so I hope you have already understood that how this GPIO write example like was happening. And in the same way, if we go to the read section, what it says is, so this was the previous one was the writing. Now we need to read some value. Suppose if some data is coming in on the GPIO port, then it will obviously try to read the value from the GPIO port. For example, if you have a push button connected to a GPIO pin and you need to read the value. Now I'm not talking about the interrupt. The interrupt processing is after that. First we have to read the value from the pin. So now what happens? So during the read, if the address bit associated with the data bit is set, the value is read. And if the address bit associated with the data bit is cleared, then the data bit is read as 0. So for example, if you see over here, it is like it's given very clearly. If you can just understand from this example here, the offset address is 0xc4. So c4 lower 10 bits would be this one 0011, and then 000100. uh, so that's like C4 what we have in the last 10 bits, and out of the 10 bits from bit 2 to 9 is interleaved, or we can say overmapped with the GPIO data. So this GPIO data is basically the data that is coming from your buttons, or maybe some kind of output input peripheral, whatever it can be. So if this is the data that is coming, so you can see that the bits which, as it said, that if the address bit associated with the data bit is set. So like for example, if we consider bit number 7, here the address bit in bit number 7 is set and the data bit is set, so we have a 1 which is returned into the input, so we read as 1. But if we consider bit number 8 and 9 of address, here the address bits are not set, so what we read is, so even if the bit 9 is set, we read it as 0, and bit number 8 also we read it as 0, right? So the same thing is also happening with bit number 6. If bit number 6 is set in the address field and the data being read is also 1, so we sense or read a 1. But here see, in bit number 5, even if the data bits are 0, even if the data bit is 1 and the address bit is 0, we do not read it into the port. So this is how we do the read operation. Basically what we see is that if the address bit that is corresponding to a data bit is 1, then we will read that particular data bit, and if it is not 1, then we won't. So let me just show you in again with an example for those who are still unclear. So okay, so here I have considered in the same way I have considered the bits. Let me just write, I have just changed the addresses a little bit. So I had taken this as CE, so 98, so I have just changed it to CE, so this will be 0xCE. Okay, now I have just taken this as a sample address, so just don't bother about this value. So what we need to do is we need to populate the bits as CE. So first we populate the E we know is in binary form, it is 1110. So this will be 1, this will be 1, this will be 1, and this will be 0. Okay, and for the C it is, we know it is 1100. So for C it will be 1 1, again 0 0, and the previous values also we keep it as 0. So now this is the address bits are here. Now let me consider some sample data bits. For example, if we are trying to read the input port and the value at the input port is F1, this F1 has come from some kind of input peripheral or buttons that is up to the system. So we will populate the bits as 1 1 1 1, and again 0 0 0 1. So this is F1. So now as we said that what we will do, we will consider only the bits which has been set in the register. So if the register bit that is corresponding to the data bit is set, then only we will read the input. So since this bit is set, this address bit is also set, this address bit is also set, and this address bit is also set. These two address bits are not overlapped or mapped, so we don't consider them. So now what we will do is, since this bit is set, we will read the input, and this input will be read over here. Since this address bit corresponding to the data bit is set, we will also read the input over here, and the same goes for these two bits as well. So the final value, we will have 1 over here, because this is 1. We'll have 1 over here, this is 0, so we'll have a 0 over here, and we'll have 1 over here, and the rest will remain unchanged. But or if we consider from the data sheet, we can see that the rest will be kept or read as 0. So the rest will be like this 0. Now unchanged means unchanged from the power up condition or the power on reset condition. So this is how the value is again read from the particular register. So this is very fast, and this helps you obtain a very deterministic input value, meaning that you can get the input at a very in deterministic latency time. So these are the very important two things that I wanted you to discuss in the GPIO section. So about the interrupt, as I told you that there is an interrupt sense register, which obviously sends that whether the interrupt is happening, and interrupt can be done at both the edges. That is, you can have interrupt at the following edge as well as in the rising edge, and you can also have an event which you register, which can be triggered when that particular interrupt happens. So all these things is very basic. You can just go through. Also, for those who would like to see that what are the steps which are involved for the initialization and configuration, remember please, like, we do not have to bother about initialization and configuration if we are using an RTOS, which is called a function called GPIO init. We can call it either inside the main thread, or we can call it inside the spawning thread. That depends on your architecture, obviously. But for those who will not be using any RTOS, for them these are the steps that are required. First, you enable the clock. So this is a very important thing that you have to remember when you are using an ARM Cortex processor core. Irrespective of whether you're going for a TI architecture, you're going for STM architecture, or you're going for any vendor, you have to enable the clock gating. That is, you have to enable the clock which is by default disabled to any peripheral. So for example, if you want to enable the GPIO 0 part or the 0 peripheral instance, then you have to enable the clock. So if you do not enable the clock for a particular GPIO, and if you want to access it, your processor will have an interrupt, and this particular interrupt will be an error interrupt, and you have to do the error handling. So first you have to enable the interrupt, you have to enable the clock to a particular port. So these are the registers, that is clock GPIO 0 clock enable, GPIO 1 clock enable. As I told you, there are 0 1 2 3 4. So accordingly you can enable the clocks. Then you have to set the direction. For example, if you have enabled GPIO 0, then you have to set the direction of the pins, which are the input pins and which are the output pins. Writing a 1 to a particular bit will be an output and 0 will be an input. If you are using as an input function, or even if you are using it as an output function, the pad register will help you control the strength of that pin. If you need a very high controlling for an LED, or if you need to source a good amount of current, or for example if you need to sync a good amount of current, so all these things can be done in the pad config register. And apart from that, there is not much more. For example, these are all the interrupt sensing, the interrupt enabling, and the interrupt masking registers. So I'm not going much more deep into it. I have just given you an overview. I expect you will go through all the registers, and in case if you want to use a no RTOS type of a programming architecture, then you have to go through all the registers. Again, if you are using a very basic kind of RTOS like a TI RTOS or free RTOS, then you don't have to bother about all these things. So these are the registers. As you can see, port 0 has an address of 40004000, like as I did assume like 40000000, but that was a sample address which I took from a TIVA microcontroller, which is another one in the TIVA family. So this is the actual address. So if I were to show you that particular design right now, then this particular bit would be 4. Okay, and this would be 4 for GPIO port A0. If you are using, so if you want to send some value to GPIO port A0, then you have to put the data in the data register. So the address value will be 4000.4000. Just ignore this dot, it just gives you an understanding of how many bits it is. It is a 32-bit address. So this will be the base address. Then again comes lower down, you can see the GPIO data register, which is this one, and the offset for that is 0. So in the drawing which I did, this offset of CE, this actually in that case will be 0. So obviously accordingly you can see like all the bits will get modified. So you can try this out for yourself. It will be an exercise for you. And Accordingly, the data will be sent, whatever data you write over here. So that is one very important part that I discussed with you. Other important registers of GPIO is GPIO direction. So in GPIO direction, obviously you can see that we have 8 pins over here, right? These 8 pins, or these 8 bits will control whether you want to configure that pin as input and output. Again, see here the offset is 400. Here on the top you can see the offset is 400. So the offset value, as I said, in our architecture, each and every register has an offset value depending on which peripheral you're using. So if you're using GPIO port E0, the base address is 4000.4000. From the base address you have the offsets, so now you can calculate which register you want to access. This is a very unique architecture of ARM. It's called a very typicality of ARM architecture. And there is also something which is called bit banding. There is also this is also part of your study, or you can just consider as your exercise. Do try to understand how bit banding works. And bit banding is something that is really important for when you want to find out that how these memory areas are actually accessed. Okay, so this I will leave to you. uh, and in later in the later videos I will try to explain what is actually bit banding. Nevertheless, if you find that if you have any queries, you are free to comment in the section, or write a direct email to me at turjashu@turjashusworld.in. Okay, so this is the interrupt sense register. As I said, that interrupt sense will tell you that whether you want to make the interrupt an edge or you want to make it a level. That is, whether you want to detect that a falling edge or a rising edge on the pin, or you want to detect that if the level is 0 volt or say 3 volts, or whatever is the higher voltage classification. So that is the interrupt sense register. Next important thing is the interrupt masking. So in the interrupt masking, you can choose that, even if an interrupt comes to a particular pin, you can prevent that interrupt from being promoted or interrupting the actual processor. So for example, if you have interrupt in pin number 1, if you have interrupt in pin number 4, and if you have interrupt in pin number 7, but if you keep this interrupt masking values as 0, so if you keep, say, the interrupt masking values for bit 7 and bit 4 as 0, so even if the interrupt happens, whatever you have configured in the interrupt sense register, even if the interrupt happens, your processor will not be interrupted. So this is like you mask it. Masking is very important when you are developing some kind of application. Suppose if any user application, you have 3 buttons, and if for any particular choice of menu the other 2 buttons has no functionality, then you can use this masking function to prevent those buttons from doing any kind of interrupt. So this is another important thing I just wanted to clarify. And apart from this, I think there is not much. Interrupt clear register is there. The interrupt clear register is something I leave up to you to study, because interrupt clear basically clears an interrupt. So whenever you enable an interrupt, listen to this very carefully, whenever you enable an interrupt for any particular pin, please keep it in mind that you clear the interrupt before you enable it, because it might happen that when you enable an interrupt, and if there was already an interrupt status pending, and without you clearing, you just enable the interrupt on that pin, your processor might just have a spurious interrupt, and then the output can become very unpredictable. So that is all about a GPIO section. This is the GPIO data register, as I said before also. So these are very few. You can see there are very few GPIO registers, and nothing much to worry about. But at the same time, if you are like trying to use, again and again I will say that if you're trying to use any system which doesn't follow an RTOS, then please do study each and every register very carefully. And there are also some mux control registers that I will tell you, because for example, if a particular pin which is already multiplexed with the GPIO and some other peripheral, you need to set that particular register first in order to make that pin be accessed as a GPIO. So that part of the lesson I will do after this. So after this I will be connecting the launchpad with the CCS, and I will show you that what are the registers that needs to be configured and how the registers has been configured. I will be using an RTOS, I will be using TI RTOS. So I won't be going deep into the register configuration. I will just show you the status of the registers when I will be blinking an LED, and that's a very simple program. That's a Hello World program wherein like I will be blinking one LED out of the three LEDs which are already present in the launchpad. Okay, so let's hang on up here with the GPIO, and I will just proceed for the next part for the CCS. Okay.